which for the purpose of stating the theorem are open and path-connected sets, and the intersection of A and B is path-connected. And X is the union of A and B. So X is made up of the two spaces A and B, but they could be um, much more complicated than just two overlapping disks like my hands. But we have a map, a diagram of maps. You see, the fundamental group of the intersection goes into the fundamental group of A, goes into the fundamental group of B, and A and B both go by inclusion into the fundamental group of X. So the Van Kampen theorem tells you that the fundamental group of X is the free product of the fundamental group of A and the fundamental group of B, modulo the subgroup of elements that must be identified in the normal subgroup generated by those elements which must be identified in order to make this work. If you had an element in the fundamental group of C, here and goes all the way over into there. So you must identify that with this. And so what we get is the following here, that you take I of an element in C, and that's in the fundamental group of A, and you take J, and that's in the fundamental group of B, and I of H times J of H inverse, or the inverse of J of H, is an element in the fundamental group of is an element in this free product, and we must set that equal to 1 because they should be both going to the same thing in the fundamental group of C. That's the least that you would need, and it turns out that's all you need to get the fundamental group of X. The fundamental group of X is the free product of the fundamental group of A and the fundamental group of B modulo the relations that you would expect. The proof involves a little path work and a little bit of point set topology, and I'm not going to give you the proof, but if you're interested in reading a proof, you can read this one or find one in another book on algebraic topology. I'm sure I have in these notes an example. We the notes to indicate an example. Here's a good example. We have the torus, and the torus can be thought of as the unit of this part B, which is just a disk. I'm calling it A. I'm sorry, B is the outside part. So the torus is the union of a disk and the rest of the torus. But the rest of the torus, if you remove the disk, is a punctured torus. And a punctured torus is easily seen to have a free group generated on two generators for its fundamental group. The punctured torus looks like two circles joined at a point. You could believe me on that one, and then we apply the Van Kampen theorem, because you see what is the element that is in common? Well, when we look at the intersection of A and B, we will get a little annulus. That's the C, a little open annulus like that, because A overlaps a little bit across B. They intersect in an annulus. The fundamental group of the annulus is C, is Z, generated by that little annulus. But what is the element in B? The element in B is A, B inverse, A inverse, B. That element right there, A, B, A inverse, B inverse, excuse me, A inverse, A inverse, B inverse, right? So I may have my arrow drawn in the wrong way. I wanted B to go this way, so it would be A, B, A inverse, B inverse. Not happy with the arrow in that drawing. But it will be a commutator. It will be the commutator of the longitude and the meridian parts of the punctured torus. And so we must set J of G equal to I of G, but I of G is the inclusion into a disk, and it's 1. So we're setting J of G equal to 1. So that tells us that the Van Kampen theorem tells us that we take the free product of the fundamental group of A and the fundamental group of B, and that's just the free group on A and B, the generators of the punctured torus, modulo the commutator, A, B, A inverse, B inverse. And of course, that just says that it's the commutative free group generated by A and B. It's Z plus Z. And you could have figured that out other ways, but this way to do it by means of Van Kampen theorem. Other example is the projective plane. The projective plane is obtained by taking a disk and identifying one edge to the other edge in this order. So that means a squared is a is identified with a inverse. And the little loop that you would get in the same argument that I just told you would be a squared. So we're going to have the free group on a modulo a squared equal to the identity, which is z mod 2z, and that's the fundamental group of the projective plane. And now we get to a more interesting example, which I leave to you as an exercise, but I may come back to it. And that is, you take a torus knot. Now, do you see that this is a torus knot? You have to examine it a little bit. It's lying on the surface of a torus. If I were to draw the torus, it would be a tube going all the way around, and this arc goes over the tube, and these other arcs are going under, and this arc goes over, and these two go under, and it goes around like that, and it's on the torus without any weaving on the surface of the torus. And you can think about making a general torus knot of type AB in a similar way. Well, then you can divide the space into the space exterior to the torus and the space interior to the torus, and the torus itself with the knot removed. And of course, you should thicken things a little bit, but that's basically the decomposition. The torus, the exterior of the torus, and the interior of the torus. The exterior of the torus is a solid torus. The interior of the torus is also a solid torus. And the space of intersection is the same as taking a torus and removing that curve. And if you think about what happens when you remove that curve from the surface of the torus, you'll see that you get an annulus. And if you then think carefully about what the Van Kampen theorem is telling you, you will see that you're going to find that the fundamental group is generated by the generator of that torus, which is identified with a to the p when it's outside and b to the q when it goes inside, where a and b are the generators of the fundamental groups of the outside and the inside, which is solid tori. That's z for generator. So it's the free product of z with itself modulo relation of the form a to the p equals b to the q. In the case of a truffle knot, it would be a squared equals b cubed. Now, you'll see this when you open up the Dropbox, just like this as an exercise, and you can try taking a look at it and thinking about it. If you have questions about this example, I'd be happy to talk about them next time. It's an excellent example to think through. And I'm showing you a few more examples that you can think about as well. We've done the knot group by using what is usually called the Vertinger presentation. This is another presentation of the knot group called Dane presentation. And in the Dane presentation, there is one generator for each region in the diagram, and the base point could be taken to be a plane, and a generator for the fundamental group goes as follows. You go down through the region, and then you come way back up through the outermost region and come back to base point. And then you can see what the generators are for that version of the knot group. And if you like, you can try using the Van Kampen theorem to prove that this gives you the generators and relations for the knot group in this way. So those are some examples. And another example that's worth thinking about, but I would only come back to it if I need it, is the first homology group understood to be the abelianization of the fundamental group. Now, you may have studied homology, and you may know the usual definitions of homology, but you can, if you like, define the first homology group to be the abelianization of the fundamental group. And then you can interpret it in terms of surfaces. And that's what the rest of these notes are about. So I've just given you a quick tour of some notes about the Van Kampen theorem and related matters that you could look at if you're interested. But don't forget the Van Kampen theorem. It's very useful to have this theorem in your arsenal when you're thinking about the fundamental group. Okay, other things that are in this box. Another box labeled Van Kampen. What is that? Oh, some notes. Okay. There is a paper in here called The Quick Trip Through Knot Theory by Ralph Fox, which was written a long time ago. And this is an excellent paper to look at, and I'm going to give you some tools today for reading this paper. You'll see that it requires some tools, although you can read the paper on its own. He talks about the group of the knot, the fundamental group. He's using the Vertinger presentation like we're using. He explains about that. And then he explains how he's going to define Alexander polynomial by using an algebraic method involving non-commutative group theory, combinatorial group theory, that he invented called the free calculus. I'm not going to explain that now. I'm going to talk about it in a few minutes. But he uses that and defines the Alexander polynomial by using that. Then, that's the part that requires a little discussion. Then he gives a series of examples. And so you have this wonderful collection of examples. Here is a knot. Here's the fundamental group of that knot. Here are the matrices that will give rise to the Alexander polynomial, and here's the computation of the Alexander polynomial, other examples of knots and computations for them, some cases of links and graphs, and their fundamental groups and so on. Then there's a section on knotted two spheres in four space and how to get at the fundamental groups of the complements of those knotted two spheres in four space, and how to think of the knotted two sphere in four space by going through hyperplane slices of the surface in four space with slabs of three space, so that in a given slab you may see a link like this, or you may see a singularity, because as you go up through these slices in four space, you may come to a saddle point or a maximum or a minimum. And he gives some excellent examples of phenomena that occur in four space and calculates Alexander polynomials and so on. Of course, open problems that are stated in these notes may be solved by now. You will have to take that with a grain of salt because this was written in the 1960s. But the paper is really wonderful for the prolixity of its examples. And if you're interested in Alexander polynomials particularly, seeing them worked out and the corresponding modules. So then there on the arithmetic of knots. And the arithmetic of knots is something that I might as well say a word or two about just from these notes for fun. If you have two knots, K and L, you can join them by making them into long knots, so it's a knot on a rope, and then splicing the forward end of one to the back end of the other, and then bringing it back around, and that's called the connected sum, or the composition of the two knots. It's not hard to see that this is commutative, and for classical knots, it's well defined. It doesn't matter where you cut it and joined it. In fact, here's the proof of commutativity. You see, you make one of them smaller and then start backing it up through the other one until it's on the other side, and that proves that this operation is commutative. And he gives a proof that you cannot cancel knots under connected sum, and I want to show you his proof. Now, it has to be understood that he is writing this paper in the topological category. So he is not worrying about proving it for tame knots, and he's willing to use a wild knot in the course of his proof. That's interesting, and you may wish to have a proof of this for tame knots. But what are we proving? We're going to prove that if the connected sum of K and L is a trivial knot, then both K and L are trivial, that you cannot cancel knots. And the proof? Well, you form an infinite connected sum of them going down to a singular point and come back around. And that is a knot. That is an embedding of a circle in three-dimensional space. And we're going to show that this knot is, on the one hand, equivalent to the L knot, and on the other hand, equivalent to K or L. You can do it for either one. And the proof, I wonder if he has a diagram of the proof. No, so we'll just point to this diagram. The proof is as follows. On the one hand, take C1 and C2 together, C3 and C4 together, and so on down the line. And C1 and C2 are given to cancel each other, and they can cancel each other by a homeomorphism that is restricted to this pair of boxes, because we started with tame knots. So therefore, you can build a homeomorphism of all of space, which takes this knot, this wild knot, to the unknot. Just build it by canceling them in pairs. On the other hand, you can leave C1 alone and take C2 and C3, and that's the connected sum of C2 with C3. It's commutative, remember? So you could just interchange them, and you could assume it goes C1, C3, C2, C4, C5, C4, and so on down the line, and then they cancel in pairs. Or you can just understand that they will cancel in pairs whether you write one way or the other. And then all the remaining pairs cancel, and you're left with C1. So that makes this knot, this wild knot, equivalent to just C1. So therefore, C1 is equivalent to the unknot. And similarly, C2 is equivalent to the unknot. And we're done. We're done by starting with tame knots and going into the wild category and showing that the connected sum of two tame knots being trivial implies that in the wild category, each knot is trivial. So what you still need to prove, if you want to get everything, is that if you have a tame knot that's trivial in the wild category, then it's trivial in the tame category. And I leave it to you to think about that. One way to try to do that would be to use an approximation theorem to make things tame. But I don't know that such approximation theorems have been written down in an intelligible way for a modern audience. You might find yourself researching all the way back to the work of Moïse if you wanted to do it that way. There may be another way. You can think about it. Anyway, this is a stimulating part of the paper, Fox. And just giving you a little tour of Fox's paper. Then he talks about covering spaces and branched covering spaces related to knots. And that's a whole topic of great interest and still is. And what else is in the paper? Cyclic coverings are a particular kind of covering. And then some group theory about the covering spaces. And then some material about the checkerboard coloring of knot diagrams in relation to their invariants and in relation to the coverings. And always lots of worked examples, some of which have very interesting properties. So this is a really great paper, and even more things about wild knots going on here near the end. It's really a wonderful paper, very stimulating, and even if you are embedded in modern techniques, the collection of examples is likely to be of use to you. So I'm putting that in there. Then there is the matter of the free calculus, and I want to give you a few minutes about the free calculus today. And then there is more about the free calculus in some notes that I have here. So I'm going to give you a very quick introduction to the free calculus, which I may begin by showing you a picture here of a covering space. We could do the whole theory of covering spaces, but I think I don't want to do that today. I will probably also, since that's also very useful background, get hold of some notes about basic covering space theory, and I'll put that in the box as well, and then that will all go into the Dropbox for you sometime in the next few hours. But here, note that a covering space, I think I should take to my iPad. Just a moment. So the basic idea for covering space, and I'm just going to be informal, is that there should be a mapping from a total space, topological space, to a base space, and you want it to be a local homeomorphism. So a good example of such a thing, never mind the rest of the details of the definition, I won't worry you about it, but that's basically what I'm looking at. And for example, I can map the real line to the circle by pi of r is equal to e to the 2 pi I r, right? Where I think of this as the unit circle in the, sorry, that's a 1, and that's a -1, and this is I, and this is -I, unit circle in the complex plane, okay? And then the inverse image of 1 is equal to the integers sitting inside of the real line. Those are exactly the places where e to the 2 pi I equals 1. So we have this going on here, 0, 1, 2, -1, -2. And if you were to take a little neighborhood of 1, then the inverse image of a little neighborhood of 1 would be a 0, and a little neighborhood of 1, and a little neighborhood of 2, and a little neighborhood of -1, a little neighborhood of -2, a stack of copies of this neighborhood here. It's locally a homeomorphism, and the inverse image of a neighborhood is a disjoint collection of copies of that neighborhood. That's a good example of a covering space. So the covering space that I want to think about here is depicted. I'm going to probably use a sketch of it, but it's depicted over here, and I kind of liked the drawing I made. So let's look at my drawing for a moment. This has got more detail than any one that I'm about to draw, but you see here I have a figure 8, 2 points, 2 circles joined at a point. And I've indicated one of them as a horizontal circle and the other one as a vertical circle. And here is a covering space of this. And in this covering space, both this circle and this circle unfurl into intervals. So what you see horizontally here is exactly like the real line covering a circle, right? This is the interval, and it goes from here to here and goes wraps once around the circle. You go here and you wrap from here to here. You wrap once around the circle here and here to here, and it's compactified. It's in a compact region in the plane, so it's getting smaller and smaller, going to limit points. Similarly for y, this vertical line here is mapping down to y, but um, but what we see here is lots of other things that are mapping down. And in particular, you can think about lifting paths in the base space and finding unique lifts of them into the covering space, none of them making cycles. So for example, you can lift x and then y. And if you do that, then you get x. And now you have to go in the y direction, so you do, and you go up here. And then if you wanted to lift x, y, x, you would go x, y, x. And then if you wanted to lift x, y, x inverse, you would go x, y, x, y, x, y inverse. And I think you can see that any word that you write in the free group here has a unique lift up into this structure, this infinite tree structure, which is the covering space above. The infinite tree structure, in fact, has the symmetries of the free group on two letters. You can shift this entire tree structure to the right by one notch, or you can shift it upward by one notch. You can shift it by x, or you can shift it by y, or you can shift it by any combination of x and y, so that the group actually is acting on the covering space. So the group theory of the free group on two letters is imaged in this covering space that we are looking at. And what I want to do is I want to think about the structure of lifting paths into the covering space. So this picture is better than the one I will sketch, but the one I will sketch lets me do a little algebra. So let's go back to my pad. We'll deal with that. So here is the base point up in the covering space. And I'm going to call this arc here x tilde, the lift of x. So you can, if you map a circle in here, then you can lift it to, if you map a unit interval in here, which goes to this circle, you will lift up into here and give you a map of the unit interval in here, but the end point ends up over there. That's x tilde, and this is y tilde. And those are the two basic coordinates in my covering space. And I can label everybody else by using the group. Let me show you what I mean. Consider this one here, this arc here. What shall I call that arc? Well, I'm going to call it x applied to y tilde, because I have the symmetry of the covering space, which goes this way, shifting by one, taking y tilde over to a copy of y tilde here. And I also have a symmetry of the covering space this way, y. So if I wanted to go up here to this arc, then this arc would be y applied to x tilde. So if I wanted to, I could think of some strange thing. Maybe x, y, x times x tilde, right? And I could locate it, right? Now let me just try locating it by looking at my diagram. First, I'm going to take x tilde, then I'm going to multiply it by x. That puts me over here. This is x times x tilde, right? Just shift it to the right. Now I'm multiplying by y. Oh my goodness, that's taking me up in here, over in here, y times x tilde. And then I wanted to shift it by x, which means to shift it this way. So my picture isn't detailed enough to handle this, but this is one of the edges. So the edges in our covering space, the edges in E are all of the form omega times x tilde or omega times y tilde, where omega is a word in G equal to the free group on x and y. All right? So that's an indexing of every edge in the whole thing. Now, what about lifting a path? Lifting a word, because you see a word, sorry. Lifting a path in B equals lifting a word in G. Formally, it's the same thing. A path in B is going around x, going around y, going around x, going around y, going around x inverse, and so on. That's some path down there, some element in the fundamental group. So then what I'm interested in is, suppose I have a word W and a word tau, then what is the lift of the product of W with tau? And I need to leave for 1 minute, so I want to let you think about that. Could you find a formula that would tell you how to lift the product of two words down in the group? Think about x, y. What's it like to lift x and y? How would it work? What would it be like to lift any given word down in the bottom? And I'll be right back. So the answer is, first you lift W. And of course, you also would like to lift tau. But if you lift tau, when I say lift, I always start my lift at the base point. So tau is in the wrong place. But if you act on it by W, you get the correct answer. Now let's take a look at that. That's the key to the whole thing. Let's take an example. Suppose I want to lift xy. Now I'm up in the covering space, right? And I'm going to get x tilde. That's the lift of x. I'm going in this order. I get x tilde. Fine. And then I'm supposed to go along and get a lift of y. Now here's y tilde. But that's not what I want. I want to be over here, right? I want to be over here in that next portion. And what is that? Well, that's been shifted by x. That's xy tilde. So you see that the lift of xy tilde is x tilde plus x times y tilde. The way we have devised the bookkeeping to label the edges is exactly according to this formula for lifting the pads. So this tells you how to lift the pads, and tells you how to get from one place to another in the covering space. Let's try another example, and let me just draw another picture of that. I'm down here, and I have a couple of things that I'm lifting, omega and tau, not necessarily the x and the y. And I get omega tilde, which takes me up somewhere, right, like that. And now I also have tau tilde, which is taking me somewhere like that, right? And tau tilde is at the base point, and I need to shift this up to here. And I ran out of, I was trying to illustrate that, and I took it too high up in the page. And so I want a copy of that same thing that I was just showing you, but it should be over here. And how do I get it to go over there? Well, tilde actually affects the transformation multiplication by omega. And that would be part of a general theory of covering spaces. But if you look at the example and the bookkeeping on the example that I'm just telling you about, then you'll see that that's exactly right. And so this is the lift here, going from here to here of omega tau tilde is equal to omega tilde up to here plus omega times tau tilde. But let's do another example. Suppose it was xy x and you wanted to lift it. So the first thing you would do is you would take x tilde, and then you need to shift by x the lifting of yx tilde, and then you would do that, and you get x times y tilde plus y times x tilde, doing it again, and then you continue your algebra a little bit, and you get x tilde plus x times y tilde plus xy times x tilde. And now let's see if we believe that by actually lifting xyx. Think of lifting xyx. So you're going to go into the covering space and you lifted x. That takes you to x tilde here. Now you're supposed to lift y, and so you have to have a little y here. But this y, this lift of y is actually x shifting the y tilde. And now you're trying to lift x, and that lifts you this way. But what kind of an x is this? This is first y times x tilde, taking you over here, and then shift it over in this direction, x times y times x tilde. It works. But now notice something else about my calculation. I can collect terms in this chain, this linear combination of edges. Each one of these is an edge, 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 edge. But I could rewrite the multipliers, and I'm going to get 1 plus xy times x tilde plus x times y tilde. Okay? Now you see, it's always going to be that way. That what I'm going to find is that when I lift a word, it's going to be equal to something times x tilde plus something times y tilde, where the two somethings belong to the group ring of G. You'll recall that we're working with this example. G is the free group on X and Y. Yeah? So we can factor out, we can collect terms, and we get an element of the group ring and another element of the group ring. Time for a new slide. So Fox's definition is that for W belonging to the free group on X and Y, and W tilde, our element in the covering space, W tilde is equal to the partial of W with respect to X, X tilde, plus the partial of W with respect to Y times Y tilde. He calls these the free derivatives. But if you're interested in computing free derivatives, of course, you can just do it by hand. Suppose I said to you again, let's try x squared y. What is the partial of x squared y with respect to x? And what is the partial of x squared y with respect to y? Well, it's equal to this. And this is equal to, we'll do it all out. And we can figure out shortcuts in a moment, but we'll it out. We need the lift of this. The lift of this is x tilde plus x times the lift of xy tilde of xy, and that's equal to x tilde plus x times x tilde plus x times y tilde, and collect terms, and we get 1 plus x times x tilde plus x squared times y tilde, and therefore we just got that the derivative of x squared y with respect to x is equal to 1 plus x, and the derivative of x squared y with respect to y is equal to, I probably made a mistake. Surely I made a mistake. Let's go back. X tilde plus x times xy tilde. No, I guess not. Not in this case. Derivative of x squared y is equal to x squared. But what are the rules? You should be able to do this by some kind of calculus on the words. So let's see what the rules should be. Well, there's really only one rule. It's this rule. Omega tau tilde is equal to omega tilde plus omega times tau tilde. That's going to tell, that's going to, you can reinvent the entire free calculus and all its rules from this. Let me show you how to do it. So we have defined dw dx and dw dy are defined by w tilde is equal to dw dx times x tilde plus dw dy times y tilde. Defined by that, right? Therefore, let's figure out what is the partial of w tau with respect to x. Well, what is w tau tilde? The w tau tilde is equal to w tilde plus w times tau tilde, and that's equal to dw dx times x tilde plus dw dy times y tilde plus w times dw dx times d tau. No, d tau. Just as bad at teaching this calculus as I am at teaching ordinary calculus. D tau dx times x tilde plus d tau dy times y tilde. We're just going to have the rules come right out, right? So we collect the terms. And what do you get? You get dw dx plus w d tau dx multiplied by x tilde plus dw dy plus w times d tau dy times y tilde. And so you see that dw tau dx is equal to this. And this is equal to dw tau dy. So by this method, Fox found a way to define derivatives on elements in a free group in terms of the combinatorial group theory. The basic derivative formula for any one of these derivatives is d of w tau is going to be equal to dw, not quite a Leibniz formula, plus w d tau. And that this formula here is just coming from w tau tilde is equal to w tilde plus w tau tilde, the basic lifting formula for paths into the covering space. And Fox, this was a great discovery. And he managed to do a lot of different things in combinatorial group theory and topology by using these derivatives, which satisfy almost the Leibniz rule, as you see. And in particular, I'm going to show you how you define the Alexander polynomial. And then we'll do an example. And then I more or less will leave it to you to go further with that if you're interested, all right? We should do an exercise, maybe. We should figure out the derivative of a power of x, maybe. Let's see what that will look like. Well, we're really talking about what's going to happen if you lift x cubed, right? So this is going to be x times lift of x squared plus, I'm sorry, going to be lift of x plus x times the lift of x squared. And that's going to be equal to the lift of x plus x times the lift of x plus x times the lift of x. And we're done. We're at an end. But now this is equal to 1 plus x squared multiplied by x tilde. So now you see that the derivative of x to the n with respect to x is equal to 1 plus x squared plus x to the n minus 1, and so on, right? And so you can learn to do calculus here. But I need to jump now and tell you the definition of the Alexander polynomial. So we are going to be given G with generators G1 through Gn and relations R1 through Rm and a surjection of G to Z, which we call phi, and this will be thought of as the group generated multiplicatively by T, okay? Now, this is always true for the knot group. Knot groups always have this. One way to understand that is, you see, if you think of the knot group of a knot, I suppose that G is equal to pi 1 of S3 minus this knot. Then this goes to the abelianization of G, and that for a single component. We're talking about single component knots. It's isomorphic to Z. Why? Because, well, because it's the first homology, if you like, but also if you think of the presentation that we already discussed, each presentation generator is of the form Z equals B inverse AB, right? And then that will go to C equals A, you see? So they all to same. And that gives you the Z. So you can see in the case of the Vertinger presentation quite directly that the abelianization of knot group is Z. And so we always have this mapping to the integers. And that's going to be the variable in the polynomial. You'll see what we do. So now this is what he does. Maybe for the sake of clarity, I'll do it this way. All right. So you let J be equal to the Jacobian matrix, D, Gi, with respect to D, wonderful, do better, DRI with respect to GJ, generators, but taking the partials of the relations with respect to the generators. That's called the Jacobian matrix, in analogy to calculus. But you then apply phi to it. That means apply phi to all the elements. And then it turns out that the Alexander polynomial of k, now that's going to be a function of t, this t, is equal to the generator of the principal, generator of the principal ideal in ZTT inverse. You can think of that, that's the group ring of Z, right? The generator of the principal ideal in ZTT inverse generated by all n minus 1 by n minus 1 minors. Of J phi, of J, okay? Now, that's the definition that Fox found. I'm not going to go through the whole theory of that definition, but I'll give you an example or two. The point is that what he discovered by using free calculus is an algebraic definition of the Alexander polynomial that comes from the group. So that this polynomial is an invariant of the isomorphism class of the group presentation. It is a way to extract this topological invariant from any presentation you have of the fundamental group of the knot. It gave, at the time, this was quite fantastic because it gave enormous flexibility in finding the Alexander polynomial. Instead of doing it by some specific representation or specific presentation of things, it allowed you to take a fundamental group, massage it into a form that you liked, and then investigate the invariant topological invariants that come from it. And that is what you will see in the quick trip. You are going to see many, many examples of working this out. But you need to see how this actually works in an example to understand what's going on. So let's take an example and see what happens. You'll recall that the fundamental group of the trefoil knot was given by two of the meridional generators only. We didn't need the third, and we had one relation, ABA equals BAB. And this is for the trefoil. And we had A and we had B, and we didn't need C, right? That's what we found before. So then the mapping phi into the group generated by T is A and B both go to T. Those are the meridional generators. Now, what about the Fox relation, though? Well, there's only one relation, but we can get at the relations. He said he needed the Jacobian matrix, But what we're really talking about is the following, see? And I should have said it in the previous slide. What we really want to look at is G with its generators G1 through Gn and its relations R1 through Rm. And we want to examine R1 tilde through Rn tilde via G1 tilde through Gn tilde. That's what's really going on. That's what we're talking about when we took the Jacobian. We're talking about all those derivatives. They are the coefficients that happen when you lift each one of these. Take a look at what happens here. And then we got a relation here. We got this is equal to this. But let's look at ABA lift. ABA lift. The ABA lift is equal to A tilde plus A times the BA lift, which is equal to A tilde plus A times B tilde plus BA tilde. There's your lift for you, and I can rewrite that as A tilde plus AB tilde plus AB times A tilde, which is equal to 1 plus AB times A tilde plus A times B tilde. All right. That's what happens to ABA tilde. And then if we take BAB tilde and we do the same thing, then we get B tilde plus B times AB tilde, which is equal to B tilde plus B times A tilde plus A times B tilde, yeah. And that becomes, let's write it out. That becomes B times A tilde plus 1 plus BA times B tilde. And now you see we are faced with the claim that, and I'll write that, BAB tilde. As far as the fundamental group algebra is concerned, if we stayed in the non-commutative algebra, we would be facing that given that this is equal to this lift into a certain covering space, which is not the universal one, but one that contains cells that satisfy that relationship. I'm not doing that whole part of the theory, but I'll speak that way. There is another covering space that's more closely related to this group, where this relation actually happens. And in there, when you lift this loop, it's the same as lifting this loop, and that means that this must be equal to this. And we're looking at that relationship, but that relationship, that this and this are the same, that relationship is kind of intractable in the non-commutative algebra. It says that 1 plus AB plus B is somehow what? A1 plus AB is somehow the same operator as B. Hard to understand, but if we translate into the infinite cyclic group, then suddenly these become much more tractable and easy relations to look at. And let's do that. Let's do that up here in this space that I have. So I'm going to apply phi to this, and then I'm going to do it like Fox did, but in my own language. So I apply phi to that. And then it becomes B tilde. Oh, wait, where is it? 1 plus T squared. 1 plus T squared times A tilde. A tilde is still just the name of the cell. Plus T times B tilde. All right? And the other one, BAB tilde, simplifying it into the group ring, becomes TA tilde plus 1 plus T squared times B tilde. Now I want you to look at that while I get another slide. we'll keep the upper part and get rid of the lower part so I can keep on calculating. So now I'm setting this equal to this. And that means I am setting in my algebra 1 plus t squared times a tilde plus t times b tilde is supposed to be equal to t times a tilde plus 1 plus t squared times b tilde. And I can collect my terms now, and I'm going to get t squared minus t plus 1 times a tilde is equal to t squared minus t plus 1 times b tilde, or in other words, t squared minus t plus 1 times a tilde minus b tilde is equal to 0. And that's the Alexander polynomial of the truffle knot. So this is the generator of the ideal of that we are after. But I'm not going through all the algebra of that. I'm just showing it to you in this way. It shows you the basic way in which we are going from the non-commutative algebra to the commutative algebra, and then being able to see what goes on. But I can say more and show you the place where the Fox theory intersects the Crumble theory, and then we will have told a story that makes sense, and you'll see that we have a Crumble definition of the Alexander polynomial that comes directly related to Fox. So stay with it for a moment, and we'll go back to the Vertinger presentation. So you understand that I'm giving you an altogether too quick survey of the Fox theory, but on the other hand, I'm telling you something that is hard to find in the literature, that the entire combinatorial group theory of the Fox derivative is all coming from that one little formula, that the lift of W tau is equal to the lift of W plus W times the lift of tau. Everything comes from that once you get your vision straight. But now let's look at the Vertinger relation. In the Vertinger relation, we have the following. And when the group goes to T, we're going to be taking A, B, and C, and so on to T. So let's find out what the Vertinger relation turns into when we take it over to this algebra. We're doing a Fox-motivated question. What kind of relation in this commutative algebra does the non-commutative relation in the fundamental group become, right? So for that, we do the lift. And so we're getting C tilde is equal to the lift of, now what about lifting B inverse? Well, there is a B inverse. So there is B inverse tilde plus B inverse times A B tilde, and that's equal to B inverse tilde plus B inverse times A tilde plus A B tilde. But now let's go back to the covering space for a moment. As if I were lifting A and B. So here would be the A tilde, and here would be the B tilde. There are more arms in the general covering space. And then you have another cell here, And this cell is B inverse times B tilde, right? But it's going in the wrong direction for lifting B inverse because B inverse goes this way. So we should have that B inverse tilde should be equal to minus B inverse applied to B tilde. Now let's see if that really works out right in terms of the way we've been thinking about this. That should be the formula for it. But we know that B times B inverse is equal to the identity. So that says that B times B inverse tilde is equal to the identity tilde. And that says that, now what is the identity tilde? That's just the zero chain. This is going to be equal to B tilde plus B times B inverse tilde. And this is equal to 0, as I said. The identity lift doesn't do anything, and it's a zero chain. Well, this says that B times B inverse tilde is equal to minus B tilde, and that says that B inverse tilde is equal to minus B inverse times B tilde. So all that fits together. All right, so this is minus B inverse times B tilde plus B inverse times A tilde plus B inverse times A times B tilde. And I want to collect my terms, and I get minus B inverse plus B inverse A times B tilde plus B inverse times A tilde. Yeah. Now what have I done? That's C. And now I'm going to take it over into the commutative algebra. And then in the commutative algebra, we're going to have C tilde is equal to minus T inverse plus 1 times B tilde plus T inverse times A tilde. I did the hard one first. C tilde is equal to T inverse times A tilde plus 1 minus T inverse times B tilde. That's the relation, and that's the commutative algebra relation. Over here, we're going to get C tilde is equal to T A tilde plus 1 minus T B tilde. I leave it to you to check. And then the philosophy here is to study the commutative module, the commutative algebra module over VTT inverse, right? But we have a new operation like the fundamental group operation, and it is a quantal operation. I have just told you a quantal operation here. This is called the Alexander Crumble by people who do quantals. So let me write it out in the next slide and you'll see what I'm getting at. The Fox calculus gives rise to the Alexander Crumble. So I will change notation slightly. So I'm going to write A and B and C, and then I'm going to say that C is going to be equal to A times B, and A times B is going to be T inverse A plus 1 minus T inverse B. And then if you had it the other way, then it's going to be equal to A star bar B will be equal to TA plus 1 minus T inverse B. And you can check that this is a quandle. And this is called the Alexander quandle. And we're going to get the Alexander polynomial directly from this rather than going through the Fox calculus if we want to. But I'm going to make one more change. Flip T to T inverse. Just because notationally I like the right-handed one to have the T. And then we will have A star B is equal to TA plus 1 minus T times B, and A star bar B is equal to T inverse A plus 1 minus T inverse B. And this is exactly analogous to our three-coloring quandle, and it's quite possible that in an earlier lecture I gave you this example as an example of an oriented quandle. I don't remember now. We could look back. But it is. You can check that A star A is equal to A, and that A star B star bar B will take you back to A, and that it works right with respect to the third itemized move. It is quandle. And it is analogous to our Fox coloring quandle. And in fact, if T is equal to -1, then you get the Fox coloring quandle. And the moral in the Fox coloring quandle was that we should look for the modulus, right? And the modulus that you want to look for here is exactly that. You want to look for the polynomial that will annihilate the polynomial that will annihilate all elements in the module. And just to see that it works, I give you an exercise, and I again have to go away for a moment. So here's the exercise. Calculate for the trefoil using this. Find out the structure of the module that you're getting when you use the trefoil, and you use those rules, and we'll do it in a second. Did it work out? Let's do it. So I'm back to the triple knot. And I'm back to my 3 generators. This is before. And I'm going to write down the 3 relations that ensue from crossing numbers 1, 2, and 3. And from crossing number 1, we have that C is equal to TB plus 1 minus TA. And from crossing number 2, you have that B is equal to TA plus 1 minus TC. And from crossing number 3, you have that A is equal to TC plus 1 minus T times B. And if you write down the matrix of this, then in the form of A, B, and C, then for number 1, you have 1 minus T times A plus T times B minus 1. For number 2, you have T times A, 1 minus T times C minus B. And for crossing number 3, you have T times C plus 1 minus T times B minus A. And just as before in the Fox coloring situation, there's a dependency, and the thing that's going to give you the Alexander polynomial is the determinant, in this case, of this n minus 1 by n minus 1 minor. This corresponds exactly to what happens in Fox. And then we take the determinant, and we're going to get minus T minus 1 minus T quantity squared, which is going to be equal to minus T minus 1 minus 2T plus T squared, which is equal to minus T squared plus T squared. Get a mistake in the minus somewhere. Being literal with what I wrote, I got minus T minus 1 plus 2T and minus T squared, which turns out to be equal to minus 1 plus T minus T squared, right? And that's equal to minus T squared minus T plus 1. And these methods only give you the polynomial up to, the polynomial is up to a product with plus or minus T to the n for some n. So there it is. There's the Alexander polynomial that we found the other way. And then another way of thinking about this altogether is to ask what relation is forced as you go around the knot. But this is the general definition of the Alexander polynomial that I'm showing you that comes out of the Alexander Crumble. In that case, you will get n in the Vertinger presentation. You get n relations and n generators, You take an n minus 1 by n minus 1 minor, and you take its determinant, and that gives the generator of the Fox's ideal and gives you the Alexander polynomial. So this is how this looks in this specific algorithmic way of doing it, and you can understand. This is just a sort of first lesson in some of these different points of view. What we showed was that you started with his general idea of the Fox calculus and specialized to the case of the Vertinger presentation. Then you get a quandle, and that quandle has its own algorithm, natural, for computing the Alexander polynomial. The next thing I want to indicate to you, and then we'll stop today on this topic, and I'll indicate something else, but the next thing you want to think about is consider the following. For a torus knot, of type Mn, the group, as we indicated before, is given in the notes, is given by A and B such that A to the M is equal to B to the N. Fox calculus will take you to an Alexander polynomial. Fast. Right? But if you think about what a torus knot looks like maybe a 4-3, here's the 4-3. One, two, three, and around. There's your 4-3. That's a lot of crossings, right? There's K4-3. And if you were to do it by the Vertinger presentation, you'd have a big matrix and quite a lot of calculation. What's going to happen here is you're going to be looking at A to the M tilde is equal to B to the N tilde, and that's going to look like at the non-commutative level, 1 plus A plus and so on, plus A to the M minus 1 multiplied by A tilde is equal to 1 plus B plus and so on, plus B to the N minus 1, then multiplied by B tilde. And then you have to think about, well, what element in the group does this go to? It's going to go to some power of t, and you have to figure out what power of t, what happens when you apply phi, but it won't be hard, and I'll put 3 dots, and you can arrive at a nice formula for the Alexander polynomial. It's actually in the notes in the box. If you want to look around in that box, I'll just say, do it, or look in the box. And you'll find that a few lines of algebra get us the Alexander polynomial of the torus knots of type Mn. So this is giving you a hint about the flexibility here that allows you to work with many different kinds of presentations. This is not at all like the modern knot theory we're about to go into with the Jones polynomial and quantum invariance and other things, but it's part of the underpinning of just about everything that happens in three-dimensional topology, that you can do this kind of thing of going back and forth between the fundamental group and various invariants. And so it's worth your while to think about this and remember that the theme, I'm going to stop now, although I was going to go on and talk about Jones polynomial and so on. But just remember that this entire lecture has been based on one little formula. All this theory of the Fox differential calculus and everything is coming from one little formula about lifting paths. So there's a central unity in this aspect of the group theoretic topology that's quite remarkable, and a research problem that I have no idea how to solve, which is how could you extend this kind of group theory approach to get at things like the Jones polynomial, things like the bracket. We don't have a clue. So this is a good place to stop for today. Questions? No questions? Okay. As I promised, I will put some more material into the box, and I will be not spending a lot more time on Fox calculus and Alexander polynomial. I will talk about one or two other ways to formulate Alexander as we go along, but next week we'll be talking about the bracket polynomial and about virtual knot theory. And I'll sign off unless somebody has another question.
Lou, may I ask you to send me your notes from the last lecture, from the last week?
They're in the Dropbox.
Okay.
Yeah.
I see.
Oh, did I neglect to send them to you? I'm sorry. I'll send you to this week and last week. Sure.
Thank you.
Mm-hmm. Okay, I'll see you next week.
Thank you very much.
Bye.